For a blog series I'm checking out control circuits, and one of the simplest is the constant current circuit. And I'll be using an example of the art of electronics where you have a single transistor current control. What we want to have here is that we can control the current going through this load. What I'm going to do is review this theoretically, so I'm going to calculate all the voltages and currents and then predict what current will be going through the load. And I'm going to do this in practice. I've set up this circuit here with different resistors, and I will go over that and see if reality is the same as what the theory says. I have a 5K resistor here biasing the diodes, and I have a 220 ohm resistor. This one will determine what the current will be through this circuit. And let's start with the theoretical approach. So the point is that we want to have the basis of the transistor at a fixed known voltage point. And when we know that voltage point here, we also know the point at the emitter, because that will be 0.6, 0.7 volts above that basis. So that's a known part. This is a diode, and that means that we can calculate that if we know the voltage here, we also know the voltage here. And if we know the voltage here, it also means that we know the current going through the resistor, because that's Ohm's law. And if we know the current going through the resistor, we know the emitter current. And if we know the emitter current, we automatically also know the collector current, because that's virtually the same. So what we're trying to do is, by selecting a fixed voltage point here and a fixed resistor here, determine what voltage will be going through the collector and through the load. And let's go through the calculations. So I have 10 volts here. That's going to be my input. And we know that we have 3 voltage drops here. So that's 3 times 0.6 is 1.8. So this is 10 minus 1.8 is 8.2 volt, if I'm not wrong. 8.2 volt plus 0.6 volt is 8.8 volt. So we know that the voltage drop here is 10 volts minus 8.8 is 1.2 volts. And 1.2 volts divided by 220 ohm is, now the film is going to break because I'm going to calculate this. And that turns out to be 5.45 milliamps. And if we know that 5.45 milliamps is running through this resistor, and we know that the emitter current is almost the same as the collector current, we know that there is 5.45 milliamps going through the collector. And that's the current that we want to control. We will check this in this setup here. I will switch this on real life and see what happens. Whenever we see a millivolt on this meter, that should represent 1 milliamp in the circuit, because I have set this device here, a microcurrent, to 1 millivolt per milliamp. So I'm going to turn up my power supply. It's 10 volts. Let's have a look what it says here. 5.4 to 5.5. And I have measured the same data points with a multimeter. The power supply is 10.05 volts. With the diode drop of those 3 diodes here, this gives us a base voltage of 8.16 volt. If I add the transistor's base emitter voltage again to that 8.16 volt, we get 8.82 volts. So over the resistor we get 10.05 volt minus 8.82 volts. That gives us 1.23 volts. And 1.23 divided by 220 ohms gives us 5.59 milliamps, 5.60 milliamps, and that is virtually the same as what we have calculated in the first part of this video.